Run. Compute the volume of the solid formed by the intersection of the surfaces. Okay, so the tech assignment is really going to kind of drive home the idea of what these quadric surfaces look like. Okay, so you don't have to instantly recognize what's what right off the bat. Once you start working through the tech assignment, it'll start becoming more second nature. That being said, size relationships are still a thing. So here we're taking, again, I edit, and then this is what happens. Should be z equals. There's a z missing.
It's on our page.
No,
On our paper it says Z.
Yeah.
It's just yours.
Okay. Well, that sucks. So anyway, you have 5 minus x squared minus y squared. So you're looking at a negative relationship here as opposed to a positive relationship. So one of them is going to be opening upwards, the other one's going to be opening downwards. If you had to take a guess which one's going to be opening downwards, it's probably the one that involves a negative. All right, so there's the educated guessing component. But there's better ways, and that's what we're going to get into. All right, so we know that the bounds are always going to be important. So there's never a bad time to start considering those. But since, and it doesn't say directly that we should do this in cylindrical coordinates, but I mean, we should, because we just learned about it. And also, there's the key indicator that I mentioned is that if I see an x squared plus y squared, that's tailor-made for cylindrical coordinates. All right? So because x squared plus y squared is equal to r squared. So I know right off the bat that I have a substitution that's ready to rock and roll. Z is equal to r squared. Z is also equal to 5. I mean, I'll just manipulate this really quickly. 5 minus, right.
I'm sorry. Yeah, 5 minus y.
If you factor out the negative, you get x squared plus y squared, which is also r squared. All right, so we have those two relationships that we can build off of, and that's going to get us into polar form. All right, since they're both equal to z, they're both equal to each other, we could say r squared is equal to 5 minus r squared. Add r squared to both sides and solve. Divide and take the root, and you get the square root of 5 over 2. With polar coordinates, we don't account for the negative because the negative is just talking about a direction. Okay?
5 plus r squared.
Would it be, say it again?
I mean 5 plus y squared.
Less. So when we pull out the negative sign here, that's going to translate. This part itself becomes r squared. So you're talking about this?
Basically, so you had the x squared minus y squared, wouldn't that equal to negative times minus?
The x squared minus y squared itself isn't anything. The negative x squared minus y squared, that's the opposite of r squared.
Okay.
Oh, okay.
All right, so dividing by 2, taking the square root, we get root 5 over 2. We don't need the negative because, again, it's a radius. If you're talking about a circle's radius, like if you go, the circle is in every direction already. If you take radical 5 over 2 steps in the negative direction, it doesn't amount to anything, right? Anything unique anyway. So this is a circle with center at 0, 0. And the radius is stated, right? So I can draw that poorly. And that's going to help me get a sense of the bounds, all right? Because I know that eventually I have to develop an iterated integral that's going to convert this over into polar form. So r's and betas are the name of the game, all right? So if I'm going to be bounded with this base area, then that's really good news because I'm looking at an entire circular region, which means that if I want to cover this region with circles, I would start with a circle with radius 0 and then increase outward until I got to a radius of root 5 over 2. Oh man, this is spiraling out of control. All right. I'm also covering the entire circle, which means that I'm starting at 0 and I'm swinging all the way around to 2 pi. Okay? It's not like that other problem where we only wanted half the circle. This time I want the whole shebang. All right? We're not given any restrictions in the problem, and there aren't any natural restrictions based off of the solution to this. So we're in good shape. I have my bounds. Now it's just a matter of having the function itself that I'm looking to integrate. Right? So what I want is, just like in Calc 2, when you're looking for the area between two curves, you want the dominant and then the non-dominant functions, and you subtract them. Same idea here. I want to take the one that's facing downward and subtract from it the one that's facing upward. Right? So in order to do that, I'm going to set up my iterated integral. I have my z equations in my polar form, which is what I want. Z is r squared, and z is also 5 minus r squared. Right? The one that's facing downward is the 5 minus r squared. Right? And it makes it look very much like a parabola when you do it this way. Right? If you put it in polar form, it becomes a little bit more obvious which one is the upward facing and which one's the downward facing. Because again, we're taking, when we go cylindrical polar form, we're taking it from 3 variables down to 2 variables. Right? In most cases, the z stays put. Right? So the x, y values converge into an r. Right? So we're looking at really 2 parabolic equations. This one faces upward, based on algebra 1, and this one faces downward, also algebra 1, college algebra, whatever. So I want the downward facing one first, and I'm going to subtract from that the upward facing one. And I'm going to multiply all that by r dr d theta. I mean, you can probably guess what the most commonly forgotten step is when it comes to stuff like this, assuming people know what the hell they're doing. Dy dx doesn't just become dr d theta. It's r dr d theta. That little r makes a big difference. All right. So we'll put the bounds in a second, but I'm going to clean this up. This part here is 5 minus 2r squared. So run it through with an r. 5r minus 2r cubed dr d theta. All right, so I know what my bounds are for r. I'm starting with a circle that has no radius, and I'm maxing out at a circle that has a radius of radical 5 over 2. In terms of the angle, I'm going around the entire circle. So I'm starting at 0, and I'm going to 2 pi. Antiderivative is not crazy because we're looking at something that is exclusively in terms of r. It's all power rule. So 5 halves r squared minus 1/2 r to the 4th on the interval of 0 to root 5 over 2. So that one step you have to do out in order to take advantage of your calculator in the next step. All right, so we're looking at 5 halves root 5 over 2 squared minus 1/2 root 5 over 2 to the 4th. Not going to bother subbing in the 0 because that's going to cancel out anyway. All right. So root 5 halves squared is just 5 halves, so 25 fourths. minus root 5 halves squared would be 5 halves squared. Again, you get 25 fourths multiplied by 1 half, 25 eighths. So that's going to give us 25 eighths. Not our final answer because I have to integrate that with respect to theta over the interval of 0 to 2 pi. Not something that we need a calculator for, as it turns out. It's just 25 theta over 8 going from 0 to 2 pi. Pop in the 2 pi. And you get 25 pi over 4. And so that would be the volume contained within those two surfaces. But it comes down to this. I mean, this is the key to everything. You don't get those bounds without knowing this. All right. So, and the reason I would know to be able that my first step should be to try to set these two equal to one another. That just comes from the idea of, well, what's going on here? You know, you have two surfaces that are intersecting each other, right? So the outer limit of the actual volume has to be wherever that intersection is, right? So it makes sense to figure that out, right? And the part that would contain the least volume would be at 0, where you haven't moved at all, right? But finding the intersection is usually step 1 when it comes to finding the bounds, right? It's right somewhere. Since I know I'm going to cylindrical coordinates, I'm going to do the transformation. Well, it's not really a transformation, but the transition from one form to another. So we know, again, that x squared plus y squared is equal to r squared. We know some other things too, but this is really the most important thing for this kind of problem. So we know that z is the same as r squared minus 3, and z would be equal to 3 minus r squared. All right, what we're essentially looking for, and it's kind of hard to see on the big screen, it's probably hard to see on the paper too, but we're looking for the outermost point of this egg, right? So by finding that intersection, we're essentially going to get that, right? And then we want to drop it down into the xy plane, all right? So r squared minus 3 equal to 3 minus r squared. All right, I'm going to add r squared to both sides, so I'll get 2r squared equals, I'm going to add the 3 to both sides, 6. So r squared equals 3, making r equal to the square root of 3. All right, again, because this is going to the xy plane, what we're looking at is a circle. Circle is not spelled that way. Circle with center at 0, 0, and radius equal to 3. Again, on the xy plane.
Roger.
Say it again?
Oh, yeah.
Radical 3, yeah. So a quick sketch of that. That is a circle, or at least an attempt at a circle. All right. If we wanted to capture that entire circle in terms of, because remember the two ingredients that we need are the r value and the theta value. So to capture that circle, we need to go out a radical 3 in terms of r, all right? And then we need to go completely around that circle. So one full turn, which is going to get us from 0 to 2 pi. All right. All right, so next step in the process would be to establish our double integral. We know we're taking one full turn around the circle. Our r value is going to span outward from 0 outward all the way to radical 3, poorly of course. And I just want to subtract my functions in the appropriate order. All right. So I want to take, if I want to capture this region here, I want to take the one that's facing downward and subtract from it the one that's facing upward. All right. So the one that's facing downward would be the one with the negative r squared. All right. So 3 minus r squared minus parentheses r squared minus 3 and that's all grouped together, multiplied by r dr d theta. All right, so we have an integral. We have our double integral. It's going to take care of pretty much everything we need. We just got to do the work now. All right, so cleaning it up, we have 3 plus 3, so 6, minus 2r squared, multiplied by the r. All right, so cleaning it, I'll just clean it up all the way before I rewrite the integral. So we're distributing that r, so we're looking at 6r minus 2r cubed dr d theta. So integrate, inside out. So 3r squared minus r cubed, r to the 4th over 2. So 1/2 r to the 4th. Okay. On the interval of 0 to root 3. The 0 is going to be irrelevant. We're looking at 9. Root 3 squared is 3 times 3 is 9. Minus 1/2 times, so root 3 to the 4th power is really the same as 3 squared. So 9 minus 9/2 would be 9/2. And so I'll integrate that over the interval of 0 to 2 pi. D theta. So we're looking at 9 theta over 2 on the interval of 0 to 2 pi.
So it's equal to 9 pi.
So it's equal to 9 pi. And either I just messed this up or I have to change my answer key. Because I'm pretty sure I didn't write that. Note to self.